Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, this is the Python part of module 4, ARIMA models. So we're going to replicate all these models. We'll talk about AR component, MA component, ARIMA and SARIMA and everything. Okay, so this is where you can find the code. Go to the GitHub repository for the course, lectures and code, and module 4. And as you can see, there are two Jupyter notebooks or Python notebooks. One is called Intuition, the other one is simply your module 4 ARIMA, IPy notebook. So basically in the Intuition one, I'm trying to replicate this. Let me actually pull up the slides one more time. So do you remember we talked about how the autoregressive component looked like? And we talked about this the phi parameter and then said if you change that phi, you're going to get different version of the AR model, autoregressive model. And we said if that phi, here we are only using one lag, right? If that phi is close to 1, basically we are getting our, in this case, random forest width drift method, right? But the takeaway from the AR model was that the AR component of ARIMA model can capture something like this. So this is what I wanted you to remember. And then the forecast is going to be something like this. For example, it increased and it converges to a number. We talked about that convergence as well, right? And then, so we want to replicate that one. So that's number 1. And number 2, we want to replicate the moving average components, right? So this is what you're going to find in the Intuition file. The module 4, AR1 and MA1 Intuition IPy notebook. And again, this is the moving average model, the MA components of the ARIMA model, and we talked about this parameter theta. If this is MA1 and if you change this theta, this is what we can model with an MA1, right? So I will start with this notebook, and then after that we're going to get into the ARIMA model. So as always, you can go ahead and open it here. If you click on this link, it's going to open it in Google Colab, but I'm going to run it on my local computer. You go ahead and feel free to run it on Colab as well. Alright, so here's that file on my local computer. I'm using VS Code, and so this is the Intuition one. I need to go ahead and select the kernels. I have this environment for the course called Deep Forecasting. In this environment, I've installed Pycaret, the latest version, the full version, Yahoo Finance, and a bunch of other packages. Okay, so but mainly we're going to work with the Pycaret one. Okay, so let's actually see if it runs. Okay, there we go. So what I'm trying to do here is replicating this slide, right? So let's go back. So this is the AR1 model. And as you can see, y is equal to a constant plus phi yt minus 1 plus some epsilon. So this is how we can, let me actually keep this one here. Again, we're creating this synthetic AR1 model and then play around with that theta parameter and see how it looks, right? So our phi is going to be 0.5, so we're going to replicate this one first. So 0.5, our constant is going to be 1 sigma. This is the standard deviation of noise term, so we're going to assume it to be equal to 1, and we are assuming that our epsilon is normally distributed, right? Okay, so let's create the synthetic time series with 100 observations. So that's why n is equal to 100, and then let's generate that process. So we start from all the values are 0. This is just a placeholder, so we're gonna set 100 zeros, and then we're gonna replace it with a process, right? Our epsilon again is it's coming from a normal distribution with average 0 and sigma. This is standard deviation 1, and we're gonna create 100 of them, right? So this is basically our yt, right? So I'm literally using this formula, yt is equal to c plus phi yt minus 1 plus epsilon. So that's it, right? So remember, this is an object. We have 100 elements in that, so we're replacing each element going from 1 to 100 by this one, right? So c plus phi multiply yt minus 1 plus epsilon t. We have to start from 1 because yt minus 1 is going to be y0. This is where the Python index starts, right? Okay, so and then we're going to forecast 20 steps into the future. So we're going to take the current value is the last observed value from the synthetic data set, right? So this is our current value. We're going to add to that current value, right? So basically we're going to use this formula on the right hand side. Hopefully you're seeing it. and then add it to the last observations, right? So this is the last observation, whatever it is, and then we're gonna from there we're gonna use this formula, right? So again, so this is going to be our forecast. Basically, this is NumPy array with 20 elements in it, and we're gonna say for steps in range of 1 to h plus 1. So basically, this is going from 1 all the way to the 20th day into the future, and this is your h, right? This step is basically your h, right? And then we say the forecasts are equal to, I'm using this formula again, so c multiply 1 minus phi to the power of step, phi to the power of h divided by 1 minus phi, plus phi to the power of h multiply the current value, right? So we're going to update that current value as we move forward. All right, so then there you go. We're going to save it in this forecast array, and then we can go ahead and do the plot, right? So the plot is pretty straightforward. So basically, this is, you're plotting your y. This is your synthetic. Yeah, there we go. This is your synthetic AR model, and these are the forecasts. We're adding it on top of it, right? So let me go ahead and run this cell and see how it does. And obviously, every single time when I run it, it's going to give me a different one, right? So I'm doing Control Enter to just show you different synthetic AR processes, right? All right, and then we know that the long-term average is what? So the long-term average is going to be if I send this h into infinity, or if it is large enough, I get c divided by 1 minus phi, because this goes to 0, this goes to 0, so it will be end up with c divided by 1 minus phi. So our c is equal to 1 here, and phi is equal to 0.5. So all these AR1 synthetic processes has a long-term forecast of 1 divided by 1 minus 0.5, which we're going to get into 2. So 1 divided by 0.5, which is 2. All right, so this means that if I just go ahead and run this cell multiple times, the long-term average is always going to be this number 2. All right, so that was the AR component. Now let's move into the replicating to the MA component, right? So here's the MA component, and we're going to replicate MA1, right? So just like the AR1, we have theta. We start with theta is equal to 0.5. And by the way, you can go back and change that theta. For example, change it to 0.99, and you will see you're going to get something close to random forest. Random walk, right? So there you go. This is your random walk. And in order to see the long-term average, because the long-term average is going to be 100, you have to increase it steps, right? So we have to say, for example, I don't know, we want to predict 500 steps into the future. So this is your long-term average. Okay, hopefully that makes sense. So I'm going to return it back to what it was. All right. For the MA component, again, the same story. We start with theta is equal to 0.5, and then our mu is 5. This is the long-term average that you want to assume for your time series AI component. Here, what do I have? Well, actually, on the slides we had 0. Here I have 5. I can change it to 0 so you see how it's going to look like. And then sigma again is going to be equal to 1. The same error coming from normal distribution, average 0, standard deviation 1. And yeah, there you go. Then the rest is just exactly like the previous one. We're creating this time series, synthetically. It's coming from this is an MA process. So your epsilon, I call it epsilon MA, just not to confuse it with the previous epsilon, but again, they are coming from normal distribution. And then this is, I call it y underscore MA, this is the MA process, and we are saving those values, right? So this is the main formula to your MA1 process, mu plus theta multiply epsilon at t minus 1 plus epsilon t. There you go. Then for the forecast, remember the long-term average forecast was pretty straightforward because we don't know the value of these epsilons in the future, so they are going to be 0 like on average. So your long-term average is going to end up always to be equal to mu. So whatever your mu had here, that's going to be your long-term average. So I can go ahead and run this one as well, and you'll see how it looks like. Okay, so this is your MA process, and as you can see, no matter how many times I run this one, or if I change these theta to large or small numbers, it really doesn't matter. The MA component always looks like this, right? So it can be 0.1, 0.9, and the average is always equal to, the long-term forecast is always equal to that mu, right? So if I change this mu to, I don't know, 5, we'll get into number 5. Okay, so let me set it back to 0, and then we can change this data to 0.5. All right, that was it. This is the intuition. I'm gonna go ahead and save it and push it to repository, so you're gonna have the latest version of this one. Now let's talk about the main Python notebook for this module. It's called module 4-arima.ipy notebook. Okay, I went ahead and increased the font size to make sure that you guys are seeing the codes and text larger. Okay, so this is our module 4-arima, and then I'm going to go ahead and open the documentation from Pycaret and SkateTime. So remember, Pycaret is a Python wrapper that's using a bunch of packages under the hood, right? Including scikit-learn, stats model, SkateTime. And then it's a good idea to have the documentation for both of these, SkateTime and Pycaret, open in front of you, as well as the source code for Pycaret. You know, we are going to look into the GitHub because we want to make changes to the functions and modules that you're borrowing from Pycaret. It's a good idea to know exactly what we're doing. Okay, so we're going to do that. All right, so again, I'm using this deep forecasting environment. I already have Pycaret installed on it, but if you're run it on Google Colab, make sure you install the latest version of Pycaret. If you do pip install Pycaret, it's going to install the light version, and in the light version, you have access to all the econometrics model. So for next module, when we are covering the machine learning models, you need to install the full version. So you need to do pip install Pycaret and then in brackets full, right? But for this one, you don't need to do that. Okay, so let's see the version of the Pycaret you're working with. At the time of recording, this is version 3.3.2. All right, so importing the libraries, we're going to work with our data set, which is airline passenger data set. Remember, you can get access to this data set either through the Pycaret package or it's available on my GitHub repository. So if you run this cell, you're gonna see the data set, right? So the index is time, month, and then we have passengers data here. Remember, time series, the first thing we need to check is the index of the data. Right now it's an object, we need to change the type, otherwise Pycaret is going to complain. So again, first things first, you have to say, okay, take this index, change it to date time, and set the periodicity to month, right? So now if you check the index, now the period is month, you can pass it to Pycaret now. Let's go ahead and import everything from Pycaret time series. Again, here is the documentation. You have to go to Pycaret, go to time series. This is basically what we're doing, right? We're going to set up the environment. Let's go. Set up the experiment and then go ahead and create model, tune model, and then we're going to look at predict model, finalize model, and things like that. I think in module 3 we talked about the details, so this is going to be a repetition of how we can do ARIMA using Pycaret. Okay. Yeah, again, as I said, the first step is time series, is setting up the experiment, and this is going to take some time. And what do we have? You're saying your forecasting horizon is 12, your coverage. Remember, guys, with the econometrics model, we can go ahead and visualize the prediction intervals, right? So the confidence level for that is 95. You can play around with this. But when you make changes here, when you do the plots, it's gonna, by default, it's gonna plot the 95% confidence intervals or prediction intervals. So I'm assuming that you have watched the theory lecture, right? In this in this Python part, we want to do something like this. We want to look at the time series, and then we will look at ACF, PACF to figure out what is the order of the P, D, and Q. And then we're going to decentralize the data to figure out what is the order for a capital letter P, capital letter Q, and capital letter D. And then, yeah, so we have a model. Then we're going to run an AutoARIMA, see if our model is close to what AutoARIMA suggests, and etc. Right? So this is basically us going over replicating what we have here. Okay, so this is airline passenger data set, and we're going to replicate something like this. All right. So I think this is pretty straightforward. You can pause the video and read through this list, but basically you're dividing your data, you're splitting data set in a train and the forecasting horizon, which is 12, or you can call it test set. In Pycaret, they call it holdout set. And under the hood, Pycaret is running some existence of seasonality, normality assumption, stationarity assumption. We're gonna check all those things, right? But it seems that Pycaret says yes, there is seasonality, and then the period is 12. So yeah, no surprise here. All looks good, so we can move forward. And there is this check stats function or method that we can call off of that experiment that we created, right? So let's see what do we have here. Remember, guys, it is important that for ARIMA model, your time series is stationary. If you have something like this, obviously it's non-stationary, and you have to use that I component, integration component in the ARIMA model to make it stationary. And then, so here, for example, if you're one differencing, then what if you need to do double differencing, first differencing and seasonal differencing? And then hopefully this is a stationary, then you can model this with AR component and MA component, right? So this is basically what we saw, something like this in the intuition file, right? So if I have a time series like this, so most probably the AR component and MA component is able to model it, right? So that's what we're doing. So the important statistics that you should look in or you should look for is, for example, we can look into Young box, and Young box basically, this is a test that, let me actually read it from here. This is a test that is commonly used to check whether there are any autocorrelation in time series. This is a very strong assumption because it says if there are any autocorrelation. And basically the null hypothesis is that the autocorrelation of the time series for lag 1 through all the way k, right? So for example, if you're including 10 lags or 12 lags, it assumes that there is zero autocorrelation. So this is tested statistics for different values of k, for example, 24 lags, 48 lags, and for different values of alpha. And as I said, this is a strong test. No, we overwhelmingly reject it, right? Especially if your time series is non-stationary, because clearly there's some autocorrelation in this data set. Actually, we can go ahead and visualize it and see that. Let me see, I think it's below, yeah. So there's clear autocorrelation. So the odds that we cannot reject this null is very low. So we can typically we overwhelmingly reject this null. Look at the statistics, it's crazy large, right? And the p-values are 0. Again, with 24 lags, 48 lags, and etc. Okay, so that's one thing. The other thing is that we talked about in the theory lecture, ADF test and KPSS test. You can use either of them. I tend to use ADF, so I'm going to look at ADF p-value. Where's the p-value? Okay, here's the ADF p-value for alpha is equal to 5%. And as you can see, p-value is crazy large. It's very large. So we failed to reject the null hypothesis. What was the null in ADF? That the data set is non-stationary. So we failed to reject that the data set is non-stationary. Yeah, and again, this is clear. Your data set is just screaming at you that it's non-stationary. Why? Because there's trend and seasonality in it. Okay, and then that's the ADF KPSS, and then finally you can test the normality of your time series with Shapiro test, and again p-value is very small, so it says that your data set is not normal. Obviously, again, this is time series. Okay, so these are some basic statistical tests that you should do when you're doing ARIMA model, right? So we can plot the data for train and test split, and this is what we want to train the model on the blue line, and we want to test it on the orange one, and we want to forecast into the future as well. Okay, so now let's talk about the parameters of ARIMA model, right? P and Q. So if you remember from lecture videos, we said that, let's go back. Yeah, we talked about this thing. Again, it's not scientific necessarily. It's just a rule of thumb. And we're going to look at ACF to figure out what is the value of Q. And we look at PACF to figure out what is the value of order P, right? And then for seasonal one, we're going to deseasonalize the data and then look at P and Q. All right, so from the plot model, we're going to look into the difference model. And again, let me show you quickly how we can get access to those things, right? So if you go to Pycaret plot model, these are different types of plots that you can do. So one of them is diff. So this is going to show you the difference plot, right? And then if you want to see what are these data quarks, always go to either go to your model container or functionals in Pycaret. So these data quarks, these parameters are typically in the functional, right? So I have to go to, again, this is the GitHub for Pycaret. And you can go to time series, forecasting, and functional. And here you can simply look for some data quarks, right? So for example, data quarks, and then search for a couple of them to find the one that you're interested in. So here we go. So this is for plot model. We can see data quarks, order list. So this is a list of, again, 1 lag, 2 lags. So this is, we're going to look into we're looking to ACF and PACF plot by one differencing, double differencing, and etc. Right? We can pass it as a list, right? We can say, actually, let me show you over the notebook. It's easier. All right. So imagine I want to look at the difference plot, and the list for that difference plot is 1 lag and 2 lag. What does it mean? It means that this is your YT. Go ahead and plot YT minus 1 for me. Okay. So this is YT minus 1. And this is YT minus 2, right? So again, 2 lag. If I set it to 3, it's going to do YT minus 3. You get the idea, okay? So let me actually run this code and show it to you. All right. So again, this is your difference plot for 1 lag. This is actually what we're interested in. And as you can see, the data has been detrended. Obviously, the original data has trend, and if I do first differencing, it's detrended. So this is as if you said your I component is equal to, your small letter d component is equal to 1, right? Again, we're talking about this one. So this one, this little d. This is as if you're detrending the data, okay? We can also go ahead and look at the deseasonalized data. Basically, if I go ahead and change this one from lag 2 to lag 12, because we have monthly seasonality, so basically this plot, this one, is now YT minus 12. So this is deseasonalized. So this is your original data set, detrended, deseasonalized. And then how do we specify, and again, so for deseasonalized, we're looking at something like this. Capital letter D is equal to 1, right? So here, if the small letter d is equal to 1, we're looking at this. Capital letter D is equal to 1, you're looking at this. And then what if we combine the two, right? What if we want both detrending and deseasonalizing? So that's where we need to use this lag list instead of order list, right? So there you go. We are going to use the plot model again. And now the data quark is going to be lag list. And I can pass a list of lags, right? So here I'm specifying 1 and 12. It really doesn't matter if you do 12 or 1 or 12, you get the same answer. Basically it says that detrend the data, deseasonalize it, or deseasonalize the data, detrend it, and then we can look at how it looks like. So this is the ACF and PACF for detrended and deseasonalized data, right? So now our job is to figure out what is the good candidate, right? So let's start with small letter p and q, right? Let's start with this, right? We know that we need this d is equal to 1 and capital letter d is equal to 1. So we know this for sure, right? Because this data has clear trend, has clear seasonality. And if you want to use MA and AR components, we have to take them out, right? So you know this for sure. And then let's work with P and Q, right? So I'm going to look at the ACF for Q and PACF for P. And basically I have to look at the detrended data. So this is the ACF, PACF I'm talking about, right? So this one, actually, yeah, let's go back. Yeah, is it this one? Yeah. So let's focus on the PACF first, right? And what do we see? We see this is lag 0, so we don't care about it because the autocorrelation is 1. Let's focus on lag 1, and we want to say if there's a sharp decline after any of these cutoffs, then that's the order, right? So lag 1, it seems that the autocorrelation is 30%. Okay, that's not small. And then the next one, lag 2, is minus 16%. So there's a clear drop off, and it seems that after that there is no significant numbers. So I would say small letter p can be equal to 1, right? So that's one thing. What about q, right? So we have to go look at the ACF for q. Again, ignore the 0, go to the lag 1. 30% going to, what is this one? Minus 17%. Again, there's a sharp decline, and the rest is pretty much, yeah, you can think of q is equal to 1, and then maybe after this 4, there's a sharp decline. Again, in terms of magnitude, we can think of q is equal to 1, q is equal to 4. These are good candidates, right? So let me actually write it down. I would say, based on the above plot, it seems that SARIMA 111. Let's ignore this part first. We're gonna talk about this. So far, we know nothing about capital letter P or capital letter Q, right? So we said 1, 1, 1. So D is equal to 1, P is equal to 1, Q is equal to 1. You can also consider Q is equal to 3 as well, right? And then how do we specify these numbers? We said that capital letter D is equal to 1 because we need to deseasonalize it. And then how do I say something about these two numbers, right? So P and Q. So I can go ahead. So you have to do it carefully. You go back to your detrended data and see if there's still seasonality spikes left, right? Both in ACF and PACF, I can tell, so this should be 12, yeah. You see for 12, there's a spike. For 24, probably there's a spike, but with less significance. The same for ACF, right? For 12, there's a spike. 24, there's a spike. 36, there's a spike. But it's decreasing, right? It's becoming less and less significant, right? So it seems that, yeah, I would say there is maybe capital letter Q is equal to 2. So I can say, because after 2, the 3 is not that significant. And for capital letter P, I would say 1 for sure. So we can do something like this, 1 for this one, and then 2 for this one. Again, this process, as you're guessing, this is very subjective. Not very, but it's relatively subjective, right? How do you read these things? But again, as I said, there are some rules. You can stick to them. But the good news is that at the end of the day, you can use AutoARIMA and then compare the performance of the model that you put together with what AutoARIMA suggests, right? So I think this one is not a bad one. And then again, to just recap, we get this one, small letter PDQ, by looking at the D trend. Capital letter PDQ, we also look at the D trend and then see if there's a spike in seasonality. If that's the case, you can go ahead and look at the D trend and deseasonalize and figure out what is a good number. So for example, look at that. This is 1 minus 30% and then 0. Yeah, I would say I'm happy with this number. And then for the other one, yeah, we can, you see you have to do it together, right? So detrend alone and detrend and deseasonalize. So maybe one is good, and based on this plot, I will definitely want to consider 2 as well, right? So yeah, then we can say we can go with this model again. Here's another candidate. Another good candidate might be SARIMA. Let's do 1, 1, 1. And then we set 1, 1, 1 again. So with 12 seasonality, right? Okay, so we can try either of them. So I would say I'm going to go ahead and create this one as my probably winning model. And then I want to use some benchmarks as well. So the benchmarks are AR1 model. Again, guys, the goal is to replicate something like this one, right? So go AR1 model, MA1 model, ARIMA 111, SARIMA 11, and again, I'm going to change it to the one that we decided to go with based on the ACF and PACF plots. And we can add the random walk and random walk with drift as benchmark as well. So our random walk is going to be ARIMA 010, so hopefully it makes sense if you have watched the lecture video with no constant. And ARIMA with random walk with drift is ARIMA 010 with constant. Okay, so these are our benchmarks. So let's go ahead and create those models. Starting with our AR1 model. So we're using this. Let me actually show you from this experiment. If I tell what are the models. Oops, we need an S here. These are the name of the models, and we're interested in this ARIMA and AutoARIMA, right? So ARIMA, as you can see, it's coming from SKTime package, and the model is ARIMA. And then how do we get access to that model documentation? Remember, I think we had it, let me pull it up here. So this is a SKTime ARIMA model, and these are the ingredients, and we have also AutoARIMA. And these are the parameters inside, right? So for ARIMA, what should we specify? We should say, what is the order? What is the seasonal order? And yeah, that's pretty much the main important stuff. And then For example, let's see, what is the scoring? We're looking at mean squared error as our loss function. Yeah, so let's go back. So basically the model name is ARIMA. Again, this is what you need to specify. Order 100, seasonality 00012. So because this is 0, it really doesn't matter what number I use here. So width intercept is equal to true and cross-validation false. By default, the width intercept is equal to true, right? So I'm going to go ahead and run this. This is going to be my AR1 model, right? So again, p is equal to 1, everything is 0, so this is AR1. What do we get? Now, obviously, for this data set, because the numbers are not close to 0 and they're all positive, I will go ahead and use mean absolute percentage error. You can look at RMSE, but for this one, it's pretty straightforward. I can trust this metric, mean absolute percentage error. So this is almost 20%. So this is a huge number. On average, our percentage error is 20%. And then we're not surprised because AR1 is not designed to model something like this. So we already know that, right? So that's why, basically, let me show you. This is what your AR1 model is doing, this red one. So you know that the performance is not going to be good in the test set in here. Okay, then the next one is MA1 model. Again, it's the same name, ARIMA 001, 00012. Hopefully this makes sense. We can go ahead and run it. And now the MAPE is even worse. It's 41%. So this is obviously not a good model either. Then we can do simple ARIMA model. So we go with detrending the data and then adding p is equal to 1, q is equal to 1, but we are not appreciating the seasonality. So let's see how it works. So this is, again, look at that. Let me actually zoom in a little bit. This is, let's go to the right, your ARIMA 111, the brown one. So it's considering the trend, but not the seasonality. So the MAPE should be better, but not that better. So MAPE is 11%. So you're making progress, right? Then we're going to look at the SARIMA 111, 12. So let me actually name it correctly. So I want to call it 111 and yeah, 112. Yeah, this is 111112. So I'm not using this 12 number. So let's say 111, 112. So this is what we put together here, if you remember. This was 111, 112. Okay. Let's see how does that one perform. So this one should do a good job, actually. Look at that. The MAPE is only 3.2%. And you can play around with these things while you're creating these models, right? So for example, do you remember we were suspicious that the capital letter can be 1 as well? Let's do that and see if you get a better number than 3.2. So let's do it. No, 4.2, so I'm going to go back to 112. Again, this was our best educated kind of guess, right? So yeah, then we're going to create our benchmarks, random walk with drift and without drift. So if you want to do random walk without drift, you have to say intercept is equal to false. Okay. So this is basically your naive forecaster. By the way, we could do this naive forecaster with something like this. Experiment, create model, naive. This is the same. The naive forecaster is the same as random walk with no drift. So ARIMA 010. Again, you can connect all these models to each other. Hopefully I watched the theory lecture and you can go back and forth between these models. So let's see how it performs for your naive forecaster. MAPE is 14.25%. It's a lot worse than this, obviously. So you're beating the benchmark. We can do naive forecaster with drift, which is a fair benchmark, more fair benchmark, which is 12.42%. And yeah, that's pretty much it. So your model that you put together based on ACF plot is doing a decent job, 3.2%. And now later on, you can go ahead and see if AutoARIMA can outperform that and then look at the details of that model, right? So I'm going to go ahead and create a list of my models, random walk with drift, AR1, MA1, ARIMA 111, SARIMA 111, 112. Okay, and then I'm going to give them some proper name. So these are the names, okay? And I'm going to run a horse race between the 5. Again, we already know the answer, but this is me showing you how we can do that, right? From this experiment, compare models. These are the list of the models. I'm not doing any kind of cross-validation here. In the machine learning section of the course, we will talk about the cross-validation. Here, it really doesn't make a huge difference because, again, This is a relatively smaller data set, and then also the ARIMA is looking at AIC, it's minimizing those metrics, and those are controlling for the fact that if you want to penalize the more complex model or not, right? So we could do that thing by cross-validation as well, but we will do cross-validation in the machine learning section of the course. You can go ahead and change it to true. I bet the ranking is not going to change in this specific case, because look at that. It says the winning model is model number 5. Which is model number 5? 0, 1, 2, 3. So 0 is index 0, and then 1, 2, 3, 4, 5. So this is our last model, which is the best one, right? If I go ahead and change the cross-validation to true, it's going to take a little longer, but again, it's going to give me a number close to this, but that model number 5 should still be the best one. Let's give it a try. Okay, while it's working on it, we can go ahead and revert it to false. Again, I'm not running it, I'm just, yeah, there you go. So basically, MAPE this is cross-validated MAPE. That one is the holdout. If I do cross-validation is equal to false, this is a test set. This one is a test set MAPE. Again, the ranking of the model is pretty much the same. All right, so yeah, this is your winning model so far. You can look at the summary of that model to write it down. So this is a summary of the model. So what do we get? SARIMA X 111, 111, and then with 12 period, right? So let's see. Look at that. The AIC is 898. And these are the coefficients, right? So actually, I can go ahead. Let's see. Where is our ARIMA model? So if you want to write down an ARIMA model, so let's do something like this. So this is the AR1 coefficient minus 0.38. So this is your phi 1. Then I have theta 1, which is 0.095. Then I have AR seasonal component, right? So this is going to be your another phi. It can be phi 2 seasonal component, right? And then this can be your theta 2, this can be your theta 3, and sigma. This is the variance of the forecast errors that your model is estimating using maximum likelihood estimation. This is a big deal because we're going to use this number to come up with some prediction intervals. So just be aware that's what we can do. All right. Okay, let's move on to plotting these models. So starting with our winning model, we can plot the forecast and change the data quarks to forecasting horizon 20, and then we can add also a label, right? So as you can see, this is showing both the forecast and the prediction intervals, right? So this is going to be the forecast in the holdout set. Now, when there's a test set, 12 observations, and then we're gonna forecast some more dates into the future. Actually, I can change it to 24. You can read it easier. There you go. So we have 12 observations here and 12 here. Overall, we're forecasting 24 into the future, okay? And yeah, just pay attention. These prediction intervals, we're going to extract them later on by looking into the predict function. But these are something that are generated using this number, right? They're, again, using this number. Okay, then we can go ahead and look at the diagnostics of this model. So basically it's going to look into the residuals and then plot the residuals for you, look at the histogram or distribution of residuals. And if you have a good model, this means that this residual should look like white noise, right? There should be no autocorrelation, no ACF, PACF, nothing, right? And as you can see, that's pretty much the case here. And this is relatively normally distributed. We can look at the QQ plot. It's not bad, but it seems that there's still a little bit of periodicity left out in the data. But again, this is the best that this model could do, right? And to be honest, it's not that bad. When I look at the diagnostic of residual like this, this is kind of okay. Okay, then for a specific model, we can run, for example, a stationarity test for residuals. Remember, if I do experiment.checkStats and then if I don't put anything, it's going to look at my original time series and then report those numbers for the time series. But if I specify a model, it's going to look at basically the residual of that model and then run some statistical test for that, right? So for example, I can run a stationarity test and look at the p-value, it's 0. So this means that your residuals are, we reject that they're non-stationary. So residuals, you can think of that they're stationary. All right. So here, just a reminder, I'm going to plot all of them. So I'm reminding you what are the models and what are the labels, right? So these are the models, these are the labels, and then we can plot all of them over each other, or we can continue plotting some of the other models as well. So for example, this is my AR one. I can go ahead and do that. Oh, I can in the data query, I can add labels and label AR1, right? This is something we're going to do later. So there you go. This is your AR1 model. And as you can see, it is converging to its long-term average. This is your MA1 model, and this is going to be basically your, this is the mu in our MA process, right? A longer term average of your time series in the train set. So that's what it is converging to. And then we can forecast all the models, right? So this is basically all the models. And as you can see, when I plot all the models, it doesn't show the prediction intervals on top of each other, because again, it's going to get confused here. So basically, it's in order to avoid that messy confidence intervals, Pycaret decides not to plot it. Okay. All right. I checked the documentation and source code. I was not able to turn it on. So if you were able to figure it out, just leave a comment or let me know. All right, so then we can go ahead and look at the prediction of the models in samples. You're not necessarily that interested in the in-sample predictions, because these models, they do a decent job in in-sample prediction, as long as, for example, you'll take into account seasonality and trend. So for example, look at this purple one. Purple one, basically we're comparing the blue line and purple, pink one, sorry, this is pink. Blue on pink, and as you can see in the in sample, it's doing a decent job, right? And yeah, that was pretty much it about doing ARIMA using Pycaret, reading a source code, and then play around with the features, right? Or parameters. Now, how can we do this thing automatically, right? Remember guys, in order to figure out what was the winning model, we call it SARIMA 111112, we had to look into the ACF, PACF of the detrended data, and then detrend and deseasonalized data to figure out those numbers, right? But what if, again, you want to do this whole thing automatically? That's where the AutoARIMA is going to become helpful. So here's the documentation from the skate time. There you go, AutoARIMA. And then as you can see, the default values are, actually they're interesting. You want to change them, right? So for example, the default value for start, small letter p is equal to 2. And you might wonder, okay, why not 1? Why not 0, right? And so we're going to change that. But the important ones are this: d is equal to, by default, it's not going to do anything. You can change it. If there's a trend in your data, you say, you know what, I have to have a trend, so I have to make sure that this is 1. If you have seasonality, you want to make sure that this one is also 1, right? Yeah, so let's go ahead and play around with this. Okay, so I'm going to create this AutoARIMA model, and the name of the model is AutoARIMA. Cross-validation false, information criteria, AIC. So again, there are different information criteria that the model is using under the hood. So that can be AIC, AIC corrected, BIC, and out of bag. These are out of bag errors and things like that, right? So by default, it's going to use AIC. I just wanted to show you how to change it. Again, you can go back and forth between that documentation. So where is it? Let's see. It was here. Here we go. Yeah, information criteria, right? And yeah, so I want to change the start point to 0 instead of 2. So start point for p is equal to 0, for q is equal to 0. Max, let's go to 2. You can change it to 3, 4, but this is going to take a while, and I'll explain you why. So, and then seasonal is equal to true. And there's this object here called stepwise, the parameter. By default, it's equal to true. Simply, if you change this stepwise to false, it's going to go over all the combinations. So it's going to take longer. So, but we know that AutoARIMA, it's going to be very computationally expensive, and so that's why by default in the skate time package and Pycaret package, this stepwise is equal to true. So this means that it's going to jump over some of those steps. And if you're curious how it's done, so let me actually show you the documentation one more time. So where's the word stepwise? Let's search step. There you go, stepwise. And we can see what it is, right? So again, this says that non-stepwise selection can be slow. Again, by default, it's stepwise is equal to true, especially for seasonal data. And you can, if you're curious, you can read this paper by Hinman and Kandakar, 2008. All right, so yeah, so this is gonna take a while, so I'm not gonna run it, or I can run it and pause the video, but this, let me actually run it and tell you how much it's gonna take. So while it's running, we can look at what we're gonna do down the road, right? So this is basically going over different combination, right? Different combination between P, Q, small letter P, and then seasonality true as well. And actually, it seems that it's using capital letter P, the default values, right? Start and max is the default value, and the start and max for capital letter Q is default value. For small letters, we changed them, right? So it seems that, it did a decent job. You know, it outbid our model. Remember, our model, our best guess was 3.2%. I think it was 3.2%. Let's quickly check it out. Where is the MAPE? There you go, 3.2%. And now the AutoARIMA figure out some model, some combination that the MAPE is only 2.3%. So it's doing a better job, but we want to see what is inside that model, right? So what were the parameters? So just keep that in mind. That's one thing. And then if I go ahead and run the default version of AutoARIMA using Pycaret, it's going to be faster. So that's why I call it AutoARIMA fast. And this is basically if you leave the stepwise is equal to true. Again, if you don't specify it by default, it's going to be true. You see how faster it was? So the older one took 30 seconds. The new one, the fast one, took only 5 seconds. And guys, remember, this is only a data set with 144 observations. So the train set has only 132 observations. So this is nothing, right? So if you have a long time series, now you're realizing that how computationally expensive is a ARIMA model, right? So just be aware. And so the faster version getting to 3.1% simply because it's skipping some of those combinations, right? And now I want to show you what are the parameters. So remember what we called it. We called it AutoARIMA. For the one that stepwise is equal to false, basically consider all the combinations, and AutoARIMA fast, the one that is going to skip some of them. Okay, so let's see. By the way, if you want to see what are the parameters of the AutoARIMA model, so you can do AutoARIMA.getParameters, params. So these are the default values. Max D is equal to 2, max P is equal to 2, and etc. etc. Okay. Okay, so let's look at the summary of that AutoARIMA, and it seems that for whatever reason, the winning model that's going to give us the smallest mean absolute percentage error is SARIMA 200111. So as you can see, this model it's basically telling you that you don't need a trend component. That's interesting, right? I like this one. The capital letter D is equal to 1 because the data is obviously seasonal, so you should have picked it up. But what about this one? There's trend, but it's not picking it up. So I don't like this model, and I'll explain why, right? Maybe, yes, performance-wise, it's better than what we put together. But intuition-wise, I don't like a model that is not taking into account the trend, because this data is clearly have a trend. So that's why I want you to learn how to do ARIMA kind of from scratch, right? Add your flavor to the model as well. Add your expert domain, the domain expertise or your knowledge to the model as well. So maybe this is performing better in the test set, but I don't like it that it's not appreciating. So let's look at the AutoARIMA fast version. So the fast version, it has a summary as well, and again, it's not appreciating the trend component. So maybe they're both outbidding your kind of subjective model, but the problem is that they're not intuitive, right? So let's look back at the model that we put together. I think it was SARIMA 111, 112. So this is the model that we put together, right? And yeah, and as you can see in the train set, by the way, in the train set, this is doing a decent job. All of them are doing a decent job in the train set. So yeah, here's the discussion that I want you to be aware. If you look at the AutoARIMA models, neither of them are detrending the data because in both of them d is equal to 0. This is clearly not intuitive for this data set because there is clear trend and seasonality. How about we force small letter d is equal to 1 for appreciating the trend and capital letter d is equal to 1 for including the seasonality. And we call this new method AutoARIMA augmented. And let's see how it performs. So I'm going to say AutoARIMA augmented. And then AutoARIMA cross-validation false, information criteria. We're not touching anything, but I'm forcing, look at that. I'm forcing these two D's, small and capital letter, to be 1. So let's run this one and see what we get in terms of MAPE. The MAPE is 4.1. So this is even worse than what we were able to put together ourselves, right? So let's go ahead and compare these models. Actually, I need to change this one to 1, 1, 2. So this is our model. This is AutoARIMA fast, and AutoARIMA augmented. And obviously the winning one was AutoARIMA. The next one was AutoARIMA fast. The next one was our model. The last one was AutoARIMA augmented. Okay, so it should be the case. So while it's running, let's see what we have. Yeah, we can look at the summary of the AutoARIMA augmented as well. And you will see that because we forced these small letter d and capital letter D to be 1, it went ahead and figured out some other model, some other parameters for P, Q, and capital letter P and capital letter Q. Okay, so yeah, this shouldn't take, oh yeah, because it is looking at AutoARIMA again, yeah, so this should take a little long. Okay, so as you can see, number 1 should be the winner. So this is the index 1, right? So this is index 0, 1. So this is the winner. The next one is 0. I don't think so. We should get AutoARIMA fast. Well, it seems that ours was the next best. So I'm missing something. Let's see. Yeah, 3.1-ish. Yeah. Well, look at the MAPE. 3.2. This one is 3.1. Well, it is sorting them based on some other parameters. So probably sorting them. Let's let it run and finish. Okay, 1 and then 0 and then yeah, 3.2. I'm curious why it is putting this one. So it is sorting. Is it sorting based on R square? Yeah, no, not this one. Yeah, it is sorting based on one of those metrics. But again, in terms of MAPE, our model is doing a decent job, right? Okay, so if you want to pick one between AutoARIMA and this one, which one do you pick? Obviously, the answer is this, right? Because again, this is the model that we had some intuition over. We said there is trend, there is seasonality, so I need a model to just include those things. Even though the AutoARIMA is outperforming in the test set, but I don't care, because this is a better model. I can explain it, I can relate to it better and things like that. All right, and again, the performance is not. Actually, it is that different. So this is 2.3%, this is 3.2%, but again, you get the idea. All right, so now let's say we can work with our either augmented model or our subjective model, whatever. So I'm going to plot the augmented model first. This is the AutoARIMA appreciating the trend and seasonality, right? So this is the forecast 36 months into the future. So there's 12-month year and 24-month year. And as you can see, the further into the future we're forecasting, the wider the confidence interval will become. That makes sense, right? Because that sigma square is a function of age. And then the bigger the age, the bigger your prediction intervals. Yeah, we can plot. Actually, you know what? I'm gonna go ahead and plot our model because this one was performing better than the augmented version. Well, let's keep it augmented because I think, let me show you something. I want to explain what's going on here. So we are plotting AutoARIMA augmented versus AutoARIMA, right? So both of them are AutoARIMA, but look at that. This one, the green one, is the one that was performing better here. Okay, the green one is performing better here. But look at the forecast into the future. This should be very alarming. Do you see that these green ups and downs are they're increasing, but it seems that the trend component is not that bold there. Obviously, there's a trend component in this time series, But if I forecast 36 months into the future, and I think if I increase it to, I don't know, 60, it will be even more exaggerated. There you go. So this AutoARIMA, because your capital letter D and small letter d was both equal to 0, is not appreciating, sorry, only the trend one was 0. The small letter d was 0. It's not appreciating the trend. But the one that we call them augmented, we force the trend to be equal to 1. So now this makes more sense now. So hopefully you realize that even though in the test set, the green one is outperforming the orange one, but for forecasting purposes, which one do you should use? Obviously the orange one. Okay. So hopefully that makes sense. And again, you can pause the video, go back, and then run these ones with your winning model, which was SARIMA 111112. What else? So in terms of in-sample performance metrics, this is pretty much the same as what we did in Module 3 for ETS models. So I'm just showing you the index of the train set, basically everything except the last 12 observation, right? That's what we specify in when we were setting up our experiment with Pycaret, right? Forecasting horizon was 12. So, and then we can make a copy of this data frame, and then we want to add the predictions, right? So YPred, these are, again, in-sample predictions. I'm going to use AutoARIMA augmented, and then the in-sample predictions, again, use the predict model for these indices. This is the index for train set, and I can calculate the residuals as well. So for residuals, we can use predict residual function, or simply we can say y minus y hat, right? Passengers minus YPred. Obviously, we can go ahead and drop the first one. Yeah, so let's do it. So this is your data frame. You have, you have actuals, predictions, and residuals, right? Okay, so this is in-sample prediction. We can drop an A's and then simply look at the metrics. So for metrics, we can do it either manually or we can borrow the functions from scikit-learn metrics. So I'm looking into R-square, mean absolute percentage error, and the two. And honestly, R-square, again, we have talked about it in previous Python lecture video as well. That doesn't make much sense, especially for time series. So I would not focus too much on R-square, but basically focusing on mean absolute percentage error. Here, I like mean absolute percentage error because look at the magnitude of your y variable, your target variable. These are relatively large and positive. So if they were close to 0, then I would be very careful with MAPE because MAPE can be very misleading. Okay. And yeah, it can be inflated significantly, which doesn't make sense. But for this one, I feel confident we can use that. So again, R-square in sample, 98% of the variation is explained by the model. Is that something that you're interested? Probably for time series not, but again, because everybody is familiar with R-square, I just wanted to report it. And what about the mean absolute percentage error in the train set? Well, 4%. So both in the train set and test set, this model is getting something around 4%, which is okay, not bad. All right, so we can go ahead and make some predictions. Again, guys, you can go back and change all these AutoARIMA augmented to your own SARIMA model, right? Actually, I can go ahead and do that if you want, or if you're curious to see how it looks like. Right, so what was the name of the model? So the name of our model, we call it SARIMA 111, there you go. So for this part, we can, for in-sample prediction, we really can use that one, right? So simply you can replace the model with this one, and this will give you the predictions of this model, okay? Hopefully that makes sense. And yeah, and finally, we are going to go ahead and make some prediction and finalize the model. So if I use this, so these are holdout period predictions, right? So basically, it's going to say predict model, and then I'm using the predict model function and basically passing my winning model or my preferred model in this case, AutoARIMA augmented. And yeah, in the test set, we already have seen this one, right? So this number was 4%-ish. So after that, we can finalize the model. So remember, Pycaret finalizing means that now use the entire data set, right, with your winning model. So let's say this is your preferred model. Instead of using only the 132 observations in the train set here, use the entire 144 observations, right? So that's what finalizing the model means. And then you can look at the, this is going to take some time. And you can also look at the summary of this AutoARIMA model. So again, we specify this D and this D is to be equal to 1. Okay. Okay, so now let's look at these. We want to visualize those final predictions. Okay, so just as a reminder, this is our data set, and now we want to use the final model to do some forecasting into the future. And guys, look at that. When I use the final model, there is no prediction for the test set because this test set was used to finalize the model as well as the train set. So that's why we don't see it here. Okay, hopefully that makes sense. If I replace it with one of the, models, so SARIMA, what do you call it? Did I use this capital letter? SARIMA, no, it's not showing up. So let's try SARIMA 111.112. Let's see if it works. No, it's not defined. How? What do we call it? I think we call it SARIMA 111, right? So let's go back. Sorry to give you a head. Okay, yeah, this is what we called it. So let's scroll down. Yep. So, there you go. You see, this is the model that has not been finalized, right? So that's why we see some predictions here. But if we finalize it, if you use the final version, what was it, the final model, then that makes sense. Okay, so and again, you can add a label, you can forecast into the future more, etc., etc. All right, so the last thing I want to show you is that how you can extract these prediction intervals, right? Remember, these are by default, well, not by default. When we were setting up the experiment, we set the coverage to be equal to 95%, right? So here, I'm going to show you how we can extract these numbers, right? So for example, the first prediction is 451.34, right? And we can create an object called unseen predictions, right? Use the predict model, pass the final model that we finalized. We can forecast 12 steps into the future. Here we are doing 24. Let's be consistent. Make this one 24 as well. This is key. So if you say return prediction intervals is equal to true, basically it's going to give you prediction intervals as well. You have to specify the coverage though. So for coverage, there are two ways you can do that. You can go ahead and simply do something like this, 95. It's going to give you 95% prediction intervals. Or you can say, you can make it, I think this is more flexible, right? You can say 2.5% from the left, 2.5% from the right. It can be asymmetric, it can be anything, right? So for example, you can say 5% from the bottom, 2.5% from the top. So but anyways, this is equivalent to your 95% confidence interval, right? So if I run this, the numbers should not change. All right. So this is your first prediction for January 61, what is it? 451.34. And then lower and upper. Okay, so there you go. These are your predictions into the future for a finalized model with lower and upper prediction intervals. That's it. After that, you can go ahead and save this model, call it my best model or best ARIMA model, and later on you can load it up. And then, so for example, if you have saved it somewhere, you can go ahead and load it and quickly apply it to your new test set that you want to make some predictions. Okay, there you go. So this is your winning model. All right, I think that was pretty much it. In the next module, we will be starting our machine learning journey for Tiemseries. It's going to be super exciting. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.